Hey everyone, and welcome. Today, we're diving deep into a fabric that's probably in your closet right now, acrylic. We're going to trace its incredible journey, starting from just a tiny little molecule and following it all the way until it becomes that cozy, wool-like material we all know from our sweaters and blankets. So here's what we've got on tap. First, we'll cover the absolute basics. What even is acrylic? Then we'll geek out a bit on the chemistry of how it's made. After that, we'll see how it's spun into thread, compare it to its cousin, monacrylic, check out some really cool new developments, and then, of course, we'll wrap it all up with the most important stuff you need to remember. All right, let's get right into it. So, first things first, what exactly is acrylic fiber? To really get why it's so popular, you have to understand its connection to wool. It was literally designed to be a stand-in for wool, and in a lot of ways, it's ended up replacing it. Okay, so on a technical level, acrylic is what we call a long-chain synthetic polymer. But the thing that really defines it, its core ingredient, if you will, is this one molecule, acrylyl. Seriously, everything about this fiber, it all starts with this one little chemical. Now, this next part is super important. It all comes down to one number, 85%. And this isn't just some random suggestion. It's the official, legal, scientific rule. For a fiber to be called acrylic, it has to be made of at least 85% acrylonitrile. Any less than that, and you've got something else entirely. And don't worry, we'll talk about that later. So, why did acrylic just explode in popularity after the 1950s? Well, it was like getting the best of both worlds. You got all that great warmth and bulk and stretchiness you'd find in wool, but then you also got all these amazing perks from modern science. It could hold these super bright colors, you could just throw it in the wash, and it didn't get those annoying little fluff balls or pills. It was just the perfect, easy care option for pretty much everything, from your favorite sweater to the carpet on your floor. Okay, now let's put on our chemistry hats for a second. How do you actually go from all those tiny, individual acrylonitrile molecules to the super long chains that make up the backbone of the fiber itself? Let's find out. It all starts with our star player, the monomer acrylyl. Just think of these as individual Lego bricks. The process that connects them is called polymerization, and it's basically like snapping those bricks together, one after another, to build a really, really long chain. And that long chain, it's called polyacrylyl, or just PAN for short. But here's a really interesting twist. Pure PAN all by itself is actually kind of useless for making clothes. Why? Because it's super hard to dissolve, and you can barely get any dye to stick to it. So, to fix this, chemists do something clever. They intentionally mix in other types of monomers, called co-monomers, right into the recipe. This creates what's known as a copolymer, and that is way more useful. So these comonomers basically come in two flavors. You've got your neutral ones, which help the polymer dissolve better and let the dye soak in more easily. Then you have the ionic comonomers, and these are the real secret sauce for getting vibrant colors. They work like tiny little magnets inside the fiber that grab onto the dye molecules and hold them tight. Pretty cool, right? And some can even give the fiber built-in flame resistance. So, how does this polymerization actually happen in a factory? Well, there are a few different ways to do it, but industry really boils it down to two main methods: suspension polymerization and solution polymerization. Let's take a look at how each one works and what the pros and cons are. Okay, first up is suspension polymerization. This is the most common method, by far. You basically just disperse the monomers in water and add a catalyst to get the reaction going. It's great because it's fast and you get a lot of polymer out of it. But there's a big catch. It creates this solid powder, which then has to go through a whole bunch of expensive extra steps: washing, drying, grinding it up, before you can even dissolve it again to spin it. It's a huge operation. The other way to do it is with solution polymerization. Now, this one is much smarter in a way. The whole reaction happens right inside the solvent you're going to use for spinning later. So you get to skip all those messy, expensive steps of washing and drying. It's a much simpler setup. So what's the downside? Well, the reaction itself is a lot slower, and it's tough to get the kind of thick, concentrated goo you need for some types of spinning. And that actually leads us perfectly into our next section. So we've got our polymer all dissolved, and it's now this thick, syrupy liquid that's called dope. The big question is, how in the world do you turn that gooey mess into a solid thread? Let's dive in. Right, so how does it work? Well, with something like polyester, you can just melt it down and squeeze it out. But you can't do that with pan. If you try to melt it, it just burns and breaks down. So we have to use a totally different approach called solution spinning. The whole idea is to get rid of the solvent, leaving just the solid polymer fiber behind. And for acrylic, there are really two main ways to do this. You can either blast it with hot air to evaporate the solvent away, that's called dry spinning, or you can push it through a liquid bath that washes the solvent out, and that, you guessed it, is called wet spinning. And the way you spin it makes a huge difference in the final product. With dry spinning, you're working faster with hotter, thicker solutions. This gives you a finer fiber that has this unique dog bone shape under a microscope, which is what makes it feel so soft and wool-like. Wet spinning, on the other hand, is slower and cooler. It creates coarser, rounder fibers that have more of a silky look and feel. So the process you choose completely changes the texture of the final fabric. But hold on, we're not done yet. The fiber that comes out of the spinneret is still pretty weak. It has to go through a whole finishing process. First, it gets a good wash to get rid of any leftover solvent. Then comes the crazy part. It gets stretched. And I mean really stretched. Sometimes up to 10 times its original length. This lines up all the polymer chains and makes the fiber incredibly strong. After that, it might get oiled up, creamed to make it fluffy, and chopped into smaller pieces. Okay, so now that we know how acrylic is made from start to finish, let's talk about what it's actually like. And the best way to do that is to compare it to its very close relative, a fiber called monacrylic. Hey, remember that 85% rule we talked about? Well, monoacrylic is what happens when you go below that number. It still has acrylonitrile, but it's somewhere between 35 and 85%. That means there's a lot more room for those other comonomers, which are specifically chosen to give the fiber some special powers. And the most famous one is being flame resistant. So if you look at them side by side, you'll see that regular acrylic is usually stronger and lighter, and it holds up great in the sun. Monacrylic is a little bit weaker and heavier. But the really huge difference is the melting point. Monacrylic melts at a way lower temperature, and that's actually the secret to its flame resistance. Instead of catching fire and burning, it tends to just melt and pull away from the flame. And this idea of adding special properties leads us to one of the coolest parts of our story, modified acrylics. This is where material scientists really get to be creative. They take the basic acrylic recipe and start tweaking it to make fibers with some incredible, specialized abilities. Take this, for example. Regular acrylic doesn't really absorb sweat very well, so scientists figured out how to build a porous, sponge-like structure right into the fiber. This creates a hydrophilic, or water-loving, version. The result? Clothes that are way more comfortable, breathable, and even feel warmer. All right, what about pilling? You know, those annoying little fuzz balls that pop up on your sweaters? Yeah, they found a fix for that too. They changed the shape of the fiber from a simple circle to something more complex. And they also made it just a tiny bit weaker. That way, if a pill starts to form, it just breaks right off instead of sticking around. And what about safety? We mentioned that standard acrylic can be pretty flammable. Well, there are two main solutions. You can either mix special flame-retardant chemicals into the polymer dope before it's spun, or you can just use modacrylic, which has that fire resistance built right into its DNA, so to speak. Oh, but the innovation doesn't stop there. Get this: bi-component fibers. This is just brilliant. They spin two slightly different polymers together, side by side, in a single thread. Then when you heat it up, one side shrinks more than the other. This forces the entire fiber into a permanent, coiled, spring-like shape. And that is the secret behind those super fluffy, high-bulk yarns you see in cozy sweaters and carpets. And lastly, check out this clever trick for dyeing. What if you want a fabric with multiple colors? Instead of dyeing it multiple times, you can just blend regular acrylic fibers with another type that's been modified to attract a different kind of dye. Then you throw the whole thing into one dye bath, and each fiber only grabs the color it's designed for. It's a super efficient way to create really complex, multicolored patterns. All right, that was a ton of information, I know. So let's take a quick moment to recap everything and go over the biggest takeaways from our deep dive into acrylic fiber. So, as we've seen, making acrylic fiber is really a story of transformation. It's this amazing journey from a simple liquid molecule all the way to a complex, high-tech fiber, and it all depends on having absolute precise control over the chemistry and the physics at every single step. So to really nail it down, here are the 4 things to remember. 1. That 85% rule is everything. It's what makes acrylic acrylic. 2. Those comonomers are the secret ingredient that makes the fiber so versatile, especially when it comes to color. 3. The spinning method, whether it's dry or wet, isn't just a minor detail. It completely changes how the fiber looks and feels. And 4, don't think of acrylic as just one thing. Think of it as a whole platform that can be engineered and modified to do all sorts of amazing things.
And that really leaves us with one final big question to think about. We've seen acrylic get engineered for comfort, for safety, for style, but what's next on the horizon? With material science moving so fast, what new superpowers could we build right into the fiber itself? I mean, could we see self-healing sweaters or acrylics that conduct electricity for smart clothes? What about a version that's completely biodegradable to help with our environmental challenges? One thing's for sure, the story of this incredible fiber is definitely not over.